this working? Great. Hi, I'm Ben. I work on loading performance.
I'm Tim, and I work on performance metrics.
I'm Annie, and I work on performance operations, benchmarking, dashboards.
And this talk is about how we aim to focus our speed efforts this year and why. I'll start by motivating our speed goals. Then Tim will talk about specific metrics. And Annie will talk about the process by which we can improve upon those metrics. So to motivate that we should work on faster loading, better responsiveness, and crashing less often, I'll focus on Chrome Mobile. These days, a lot of browser instances are on mobile devices, and the mobile context is particularly constrained. Okay, so this slide shows the fraction of Chrome mobile browsing sessions on each of several different connection technologies, like 2G or 3G, 4G. In the United States, India, Indonesia, and Nigeria. The breakdown in the United States is what we're all accustomed to. Users are on fast networks practically all of the time. 59% of browsing sessions are on Wi-Fi, 37% are on 4G. Now look on the right side of the graph. Compare that to Nigeria, where 86% of browsing sessions are on slow connections, 3G or poorer. 77% are on 3G, 7% are still on 2G, and 2% manage to browse while completely offline. India and Indonesia have better connectivity than Nigeria, but significant fractions of sessions are on slow connections there as well. 17% in India and 37% in Indonesia. Note also there's a significant bias to this data. Users attempt to browse more often when they know their connection will be fast enough to support web browsing. So the landscape of what users really encounter is actually much worse. The devices that people use are also exceedingly constrained. Roughly a quarter of Android devices in the first half of last year were sold for less than $100. To sell a device that cheaply, all corners have to be cut, including RAM. In Nigeria, for example, 60% of devices in use have less than 1 gigabyte of RAM. This is at or below the minimum set by Android spec. And with a glut of cheap, low RAM devices entering the market, this situation is likely to get even worse. Finally, pages keep getting bigger. This graph from HTTP archive data shows the average transfer size of mobile pages over time. The current size, 3.2 megabytes, is approaching double what it was in just 2016. Okay, so together, when networks are slow, devices are constrained, and pages are increasingly more complicated, pages load painfully slowly. Okay, so how bad is it? I'm going to try to play a video to show you how bad it is. So this is an example page load on a Nigerian 3G network. And I'll press play. Okay, so lots of white. Still white. White. Okay, now things are showing up around 5 seconds. This is actually a faster than typical Nigerian 3G load. We're still waiting for the page to complete loading. Still waiting. Finally, that ad pops in. So think about this. How much would you use the web if every page took that long to load? Okay, but I thought the web was fast. So this is a distribution of the time from navigation until anything at all shows up on the screen. This is really first contentful paint. And the median is 1 second. That seems fast, right? But look, there's a pretty wide distribution. And if we go out to the 95th percentile, suddenly we're at 6 seconds. That's 6 seconds waiting for anything to show up on the screen. The time to interactive, or the page being usable, is typically around double that. And so you might say, oh, so what? It's the 95th percentile. 95th percentile means 1 in 20 loads takes at least 6 seconds before anything shows up. To pick on Nigeria, in Nigeria it's double that. 12 seconds to that 95th percentile to first contentful paint. So you might say, okay, well, that's Nigeria. We're in the United States. We don't care. It's we have data that shows that most people around the world experience at least one of these painfully slow loads once a week. And with that, I'll turn it over to Tim.
Sorry, it told me to locate my cursor here.
I couldn't find it either.
All right, I guess it's gone forever. All right, so what do we mean by speed? When we refer to speed, we're really referring to all user-facing aspects of performance. So obviously, this is going to include things like page load time or animation smoothness. But for some users, it absolutely includes things like power, bandwidth consumption, and memory. If you're on a beefy desktop with 64 gigs of RAM and you're plugged in and you've got an unmetered Ethernet connection, these aren't really user-facing. But if you're on a phone where bandwidth isn't expensive, you've got 15% of your battery life left, these are absolutely user-facing aspects of performance. We've been trying to figure out how we can ensure we're tackling the speed issues which impact users the most. Oh my goodness. Annie, could you attempt to locate the cursor while I continue speaking? Thank you. We've been trying to figure out what speed projects we should tackle. There's lots and lots of interesting speed projects to do, but we only have a finite amount of resources. Hey, success. Thank you. So we believe the best way forward is to align on what needs fixing. We don't need to push super hard on aligning on exactly how we fix the problems. Ideally, we'd have everyone in perfect agreement, but there's a lot of us. And so we think what's important is to align on the objectives. And we think these objectives are best described with concrete targets for specific user-facing metrics. We've come up with a proposal based on our understanding of what successful speed projects are already doing. We'd love to hear your thoughts on this. Feel free to grab us to chat later on or send us an email. We're currently focused on getting alignment on this across the Blink team, but hope a similar approach will work for Chrome more broadly, and some of this is already starting. Our speed goals for 2018 are to load fast, be responsive, and not run out of memory. And we have a particular focus on low-end Android devices, as Ben justified earlier. A surprising number of our devices are low-end. So when we're trying to measure whether or not we're loading quickly, the current metric we use is first contentful paint. You can think of this as a lower bound. It's the first time we rendered something the user maybe could care about. In this example, it's clearly not perfect. We're rendering the search results page, and we say first contentful paint fired before any search results are showing. This is not perfect, but first contentful paint is the best paint metric that we have in the wild, and in aggregate, it tends to work pretty well. First contentful paint is defined as the first time the browser rendered any text, image, non-white canvas, or SVG. So here you can see we're tracking our objective for 2018. We're tracking the 99th percentile on Android. We're currently at about 15 seconds and aiming for about 12. The x-axis here, which you can't see, is time starting from January 1st up until approximately today. So you can see there's some weekly variation around 15 seconds. We've got our target there in red at 12 seconds, and thus far we haven't really made much progress. But we do have some exciting stuff planned in terms of loading optimizations for the rest of 2018. So we're hoping we'll be able to hit that 12-second objective. When we're trying to measure whether or not we're being responsive, the metric we use right now is expected queuing time. When a user interacts, we want to make sure the page can respond instantly. It's really difficult to cover all of the different types of input in a single input latency metric. Expected queuing time isn't quite as user-facing as some of our input-specific latency metrics, like, say, touch scroll updates or that sort of thing, but it is the most general. It covers a large variety of kinds of interactions, basically anything that hits the main thread. We know that main thread queuing time is the primary contributor to input jank, and so expected queuing time is a proxy for the time taken to respond to events which block on the main thread. We define expected queuing time as the expected, so like the average duration, an input event would be queued on the main thread for an input event arriving at a random time within a window. So we can say over this 1 second interval, if an event arrived at a random time, what's the average amount of time it would be queued on the main thread before we can even start processing it? In UMA, so the data that we gather from the wild, we report expected queuing time once per second per process. The picture here is not great. So this is a graph for Android devices with 512 megs of RAM, looking at the 99th percentile of expected queuing time. And so you can see right now we're at about 1.5 seconds, trending upwards away from our goal of 1.1 seconds. This is mainly due to an M65 regression that we're digging into. And I've got high hopes that things like cooperative scheduling, out-of-process iframes, those sorts of things are going to make some positive impact here. When we're trying to quantify how often we're running out of memory, we use the number of renderer crashes on Android per million page loads. So we care a lot about out-of-memory crashes because they're a massive disruption in user experience. Even when this is extremely rare, it's still terrible for the user. This is obviously primarily an issue on low-end Android devices, but they're becoming increasingly more plentiful. This isn't the only concern with memory. Memory use can also kick other apps out of RAM, that sort of thing. But most of the changes that we're making to improve the out-of-memory crash situation also improves these other situations. This graph is looking pretty good. So this is for 512 megabyte Android. We're looking at out-of-memory crashes per million page loads. And we've got a slow trend downwards towards our objective of reducing from 1,500 crashes per million page load to 800 crashes. The three metrics we just talked about are kind of the primary metrics we're aiming to drive down as the Blink team in 2018. But there are a bunch of other metrics that matter. And we'll go over a few additional metrics which speed launches should track. Scroll begin latency. When we refer to scroll begin, we're referring to the first frame the screen updates in response to a user scroll. And by scroll updates, we're referring to all the subsequent frames that we respond. We track scroll begin latency and scroll update latency, and we also split this out by what caused the scroll, whether it was touch input or wheel input, that sort of thing. In all of these cases, we measure the duration from the event's hardware timestamp until we update the display with the scrolled offset. There are also a few up-and-coming metrics we're excited about, but that haven't been proven to the point where we want to set explicit goals on them. You might want to include these metrics when you're evaluating features you're working on to get some additional signal or potentially to offer us some feedback in developing the metrics. Lack of interactivity during page load is an increasing problem on the web. As we've incentivized developers to paint quickly using metrics like first contentful paint, they've sometimes accomplished this at the expense of other things like interactivity, which we didn't have good metrics coverage of. In the bottom right here, you can see an example where we're loading a page, and the page looks usable. It looks great. But as the user sits there tapping and tapping and tapping, the page isn't responding for seconds. And so we now have two new metrics which are designed to capture the pain that users feel in these experiences. The first of these is time to interactive. When the page is ready to process input within 50 milliseconds. This is kind of when the page is quiesced. Unfortunately, we can't measure this accurately in the wild. So in the wild, we're using a different metric, first input delay. This is the queuing delay of the first user input. So this captures the very first time the user interacts with the page, how good was the user experience? We did a correlation analysis where we look at time to interactive in the lab versus first input delay in the wild, and we were quite pleased by how closely they correlate. So in order to, we've talked through our 2018 speed objectives. The next question is, how do we actually use these objectives in order to decide whether or not to pursue a speed project? How do we actually use this for prioritization? And we end up applying these in kind of different ways depending on the kind of speed project. We've broken up the kinds of speed projects within Blink into 3 main categories. Obviously, there's optimizations, where we're just making the existing web faster. A great example of this is throttling JavaScript in background tabs and off-screen iframes. Interventions in general fall into this optimizations bucket. They're just optimizations which have some kind of compatibility risk. New primitives, when we're just shipping a new feature that enables us to build faster pages. I think a great example of this is animation worklet, where we're providing a new feature which lets web developers rewrite their page to be faster. Instead of animating something on the main thread, which is potentially going to be slow and janky, we're going to let them use this new feature, animate on the compositor thread, which has better performance characteristics. And finally, there are activation projects. So this is where we have an existing feature, but adoption is limited because the performance of the feature isn't that great. We've seen some problems here with Service Worker where we've had performance issues, and there's performance work that goes into just enabling more adoption, and we consider this activation. So we decide whether or not we should invest in these kinds of projects in different ways. For an optimization project, the primary question we want to answer is, will this contribute to our overall speed goals? So ideally, we want to kind of align our optimization efforts to focus on those 3 main objectives for 2018. The second question we ask is, can we actually demonstrate that we're improving these core metrics we care about? So we want to do an A/B test. We want to launch the feature to a fraction of our population and see, did we actually make that fraction of the population's user experience better on these key metrics? Now, this isn't to say that you should never do any performance optimization work that doesn't contribute to those top-level goals, but we definitely want to be aware of how much time we're spending investing on things that aren't contributing to the super high-level objectives. When we want to ship a new primitive, our hypothesis is, if we ship this primitive, some page is going to adopt this primitive and it will make their page faster. In order to verify this, we want to have as many as possible of our new primitive launches where the goal is performance, to have a launch partner sign up and say, I will use this feature in an origin trial and report back to us with data. Were they actually able to make their page faster using this new primitive? Activation is a little bit unique in that activation work can be important without directly contributing to our overall speed goals if it's enabling increased usage of a feature which is important for non-performance reasons. So it's a bit of a special case. And yeah, again, I think a great example here is Service Worker. Service Worker partnered up with Facebook, and they actually gave us some feedback that they were having some performance problems, proposed the navigation preload idea, and were able to see some performance improvements through navigation preload. So our hypothesis is people aren't adopting this because it's not fast, and so the goal is find someone who says, we will adopt this when it's fast, and enable them to adopt the feature.
So I want to talk a little bit more about optimization projects, specifically the tools and processes that we have in place to help you all the way from idea to launch. And the first thing I wanted to talk about is reiterating what Tim said on the last slide about optimization projects. How do we evaluate the impact when they're done? And the first important point is that we evaluate the end user impact of an optimization project. Why is this? Well, obviously, like, these end users that we're trying to help, those actual people on their phones in Nigeria. But if you take a step back from that, there's actually like hundreds of millions or more end users, billions and billions of web pages, languages, different countries, lots of different network connections. It's pretty much impossible to predict the impact of your change with a benchmark or some local measurements. You really need to be looking at the end user impact. And then secondly, I wanted to talk, just reiterate that although it is good to do optimizations no matter what, if you can show impact on the speed launch metrics, it's a really good focusing factor for making sure that we're really getting end user visible projects and we're focusing on what the user is, how it's going to impact the actual user. Of course, you might have sub-metrics or like specific metrics for your code, and that's awesome, but hopefully we can have a lot of projects that drive down page load time, out of memory, et cetera. So how do you measure the end user impact of your performance optimization on the speed launch metrics? So the answer is to start with the Finch trial. Finch is Chrome's experiment framework. It allows you to have a variation of Chrome's code that you can send to actual end users and compare with a control group. So you can basically look at all of the speed launch metrics, plus all the other UMA metrics, like your own project's performance metrics, stability metrics like crashes and user data on your experiment versus a control. One thing to keep in mind with Finch is that you should always check, especially performance metrics, for statistical significance. If you see a gray box, you should adjust the volume, adjust it upward so that you can be sure something is statistically significant, but try to be careful not to crank the knob too high until you're pretty confident in your experiment. Another thing that you can do is turn the experiments on and off in a config file so that they get turned on as a whole on the performance bots and also all the correctness testing bots. One thing we see a lot is somebody's change causes a performance regression, and we want to revert the CL, but they want to add a bunch of things on top of it because that's simpler. If you have it all inside a Finch experiment, then you can just turn the Finch experiment off on the bots and turn it on and off as many times as you need to see if it's met your goals. Unfortunately, Finch experiments can only be configured by Googlers. If you're a Googler, you can go to Go Finch 1-on-1. If you don't work at Google and you'd really like to still launch an experiment this way, you can ping speed@chromium.org to see if it's possible to partner. Next, I want to kind of go over the whole story from beginning to end of how we launch speed optimizations. And you can kind of think of these steps as like a sieve. We can throw out ideas that don't work even before we've submitted the code or fully implemented it. After it's landed, we can find performance regressions we didn't expect. When we're launching, if it's not having any impact, or if it is having an impact, but it's a trade-off, we can address it then. And if regressions get through after launch, then we can follow through on them. So first, before you even write some code, one thing that I wanted to highlight is Traceviewer. It's Chrome's performance analysis tool. If you haven't used it, you can go to Chrome Tracing and click record, and you can record anything that the browser's doing. So loading a page, scrolling, whatever. And then it gives you this overview of what's going on. So the x-axis is time, and then at the top you can see CPU usage, and then you can see all of the different processes listed out with everything that's going on in each thread. In this example, I loaded the Dromeo benchmark page, and I click run. And you can see there's a bunch of activity when I loaded the page, and then V8's really pinned down running the benchmark. You can click on any of the samples to get more information about what Chrome's doing in your trace. And this is a really good way to just get an overview of what's going on in an area you want to improve, or if somebody shows you a website that's doing something really unexpectedly slow, it's a great way to dig in. Next, I wanted to talk about our benchmarks. Specifically, we've been working really hard to keep up with the speed launch metrics work, and we have the system health benchmarks that measure all of the speed launch metrics, both on desktop and on Android. And we made a really big effort to get some very popular web content and measured in about 90 minutes of real-world use cases of users, interacting with pages. And another thing to keep in mind, you can run those locally, but many of us have pretty beefy developer workstations. If you want to run on a low-end phone or a lower-end laptop, you can use the Perf Trial bots to send a job to run any of our benchmarks on an unsubmitted CL. If you want to expand to a lot more web pages, and then we have a very, very large corpus of documents in cluster telemetry, so we can measure all of those same metrics on a much larger study on a change that's not even submitted yet. Unfortunately, again, only Googlers can run it, but if you ping speed@chromium.org, we can help you run a job. So you've done some experiments, you think this is the right thing to do, you land the code either just directly as a CL, or you turn on your experiments on the bot. After you land, we have the Perf Waterfall. It runs about 30 hours of tests on each of over a dozen different device configurations on all our different platforms. And the Perf Dashboard collects all that data, it automatically detects regressions in time series, and groups them together. And then after that, Perf sheriffs file bugs on the regressions, and it can bisect down to individual CLs. If you want to see how your specific CL impacted all of the Perf Dashboard measurements, you can go to this URL here and type in your commit position. We're working hard to make this easier, but right now, if you want to find out like if your commit caused that improvement, you'd have to bisect it yourself. Otherwise, the perf sheriffs will do the bisecting. All right, so now you want to start launching your experiment. You do that by enabling the Finch trial and ramping up the volume. One thing that I really wanted to call attention to that not a lot of people are aware of is the heartbeat tab in Finch. That actually contains all of our system health metrics, or our speed launch metrics that Tim just went over. So you can see them all listed in one place and how you're impacting all of them. And you can also slice by platform, device characteristics, things like that. So hopefully, you follow the process, you launched, everything went well, but I think a lot of times we still see regressions in the wild that we didn't expect. And so we have a couple of different processes I wanted to make people aware of that we use to make sure that we can address any regressions we see. First, there is a group that looks at the UMA metrics for all of Chrome, like the graphs that we showed earlier, and tries to identify root causes for regressions. If you use the Finch trial, it's very easy for us to rule out your change. If not, we usually end up being able to go down to the canary build and look through the CLs. So if you get a ping on one of these bugs and it's asking, what does your CL do? Could it have caused this? It's really, really helpful if you can respond and let us know, give us any information you can. We have a couple more fine-grained tools that we're using. First, was mentioned earlier, the out-of-process heap profiling. It takes anonymized heap dumps for the wild, and it looks for unexpectedly large allocations. And so you might get CC'd on a bug if you own a piece of code or if you recently changed a call stack that it found is allocating memory. And like I said, it can drive down memory a lot if you can respond and try to figure out, like, maybe this code could be leaking somehow. We have a very similar process for the sampling profiler. Currently, it's looking at startup, but it probably is going to expand soon. This measures execution time, and it can tell you if, like, a certain function might have been running longer or a certain stack. So again, if you own the code or if you've recently changed the call stack, you might get a bug on things like that.
Okay, so following what Annie said and what Tim said, at a high level, there are several directions we can take to actually improve on speed. We can optimize Blink. We can intervene when a page is constructed poorly and make it faster. And then we can also provide new APIs or restrictions, like feature policy on those APIs, to encourage using best practices. I'm not going to go through the rest of this slide other than to point out that there are a number of brainstorms and talks over the next 2 days that talk about speed specifically. So I encourage you to attend. These are the ones I noticed in the list. I'm sure I've missed some.
One quick addition is we have a feedback session on the metrics and also the operations stuff that I just covered immediately following this talk in Box Elder.
Thanks.